In this video, we are going to do linear approximations and differentials. So we are going to use slopes of tangents to find a linear approximation of a function. So here is a formula you are going to need to know, that the linear or tangent line approximation of f at some value a is L of x, which is given by f of a plus f prime at a times x minus a. And we call that L function the linearization of f at a. So we've got this function here, and if we want to approximate what's happening at a, we can use the slope of our tangent as an approximation. Now, some functions lend themselves to be more exact approximations with the linearization formula than others, but it is an approach that can be taken for values that are close to something we know. We can help kind of pinpoint approximately what is the value we're looking for. So I've copied the formula down here, and let's look at example number 1. It says, find the linearization of the function f of x equals the square root of x plus 3 at a equals 1. Now let's think about the fact that the square root of x plus 3, if our x value is replaced with an a value of 1, we know the square root of 4 is 2. And what this is going to do is it's going to allow us to approximate the numbers of the square root of 3.98 and the square root of 4.05 because they're close to a square root that we're going to know. Okay, and are these values overestimates or underestimates? We'll find that out in a minute. So if you look at this formula, there's a few things we're going to need to know. Okay, so what is f of a? Well, f of 1 in this particular case is the square root of 1 plus 3, or the square root of 4, or 2. So we need to know that. We need to know f prime of a. So we need to know f prime of a. So let's take our derivative. So I've rewritten this so that I can use the chain rule pretty nicely. I'm going to drop the power, leave the stuff alone. Power goes down by 1 times the derivative of the inside. Now this derivative is nice, it's just 1. And now don't even worry about simplifying, because if you got to plug a number in, why not plug it in? So that's 1/2 4 to a power of negative 1/2 times 1, or 1/2 times 1 over the square root of 4, which is also 1/2 times 1, or 1/4. So now we have all the pieces we need to stick into our formula. So let's go ahead and do that. So what we get is that our linearization is f of a plus f prime of a times x minus a. So we get this is 2, this is 1/4, this is x minus 1. So we get 2 plus 1/4 of x minus 1/4, or so we get 1/4 x plus 1.75. So that's our linearization. So let's think about what our original function was. Our original function was the square root of x plus 3. So if we want to get 3.98, we have to input 0.98. If we want 4.05, we have to input 1.05. So this is going to tell us what we want to input into our linearization formula. So I need 0.98 to get to the value I want. I need 1.05 to get to the other value I want. Okay. So let's do each one. If I do plug it in 0.98, I get 1/4 of 0.98 plus 1.75, which is 1.995. Now, if you were actually to do the square root of 3.98 on a calculator, it's approximately 1.99499. So this is a little bit over. Look how close it is. It's pretty darn close. If we do it again, if we plug in 1.05, we get 1/4 of 1.05 plus 1.75, which is 2.0125. If we really were to square root 4.05, we get 2.0125. No, 2.01246. So this, again, is just a touch over, but look how close it is. It is so accurate that if we rounded the original to the 4th decimal place, they both match. So, it is a pretty darn accurate thing to use this approximation. So that is our first example. Then there is something called a differential. So you might recall that f prime of x, so is the derivative of y in terms of x, could have been written like that, dy over dx. Think about if we separate those two things and we cross multiply, the dy, or the differential in terms of dx, is f prime of x dx. So dx is the independent variable, dy is the dependent variable, okay? And here's a little illustration of how dy and y prime, or dy dx, is listed on there. Now, this is just a formula, so don't make it harder than it has to be. In part A, it says compare the values of delta y and dy if y is x cubed plus x squared minus 2x plus 1. Now we're going to look from 2 to 2.05, and then we'll look from 2 to 2.01. Okay. So what we're going to do is we are going to look at this formula to find dy in terms of dx. Okay, so think about the fact that f prime of x for this particular function is 3x squared plus 2x minus 2 dx. So if we were to take the function and plug in 2, we get 9. If we were to take the function and plug in 2.05, we get 9.717625. So the change in y is just our ending value minus our beginning value, or 0.717625. Okay. Now let's go ahead now and talk about what is dy. Okay, so let's think for just a minute about what we know. Our x started at 2 and ended, so we're going from 2 to 2.05. So our change in x is 0.05. So for this particular case, we're just going to make that value our dx. Now remember, our x value starts at 2. So our dy is going to be 3 times 2 squared, which is 12. 2 times 2 is 4. minus 2 times our change in x is 12 plus 4 is 16 minus 2 is 14 times 0.05. Our change in y is 0.7. So if we compare those two, our delta y, our exact change is 0.717. Our dy is 0.7, which are very, very, very close quantities. So you're welcome then, this is just showing you can calculate it both ways. Now, let's look as we get from 2 to 2.01. So when that's the case, f2 we know is 9. F of 2.01 I've done earlier, it's 9.140701. So our delta y is that 0.140701. Now, delta x is just dx. So if we're going from 2 to 2.01, delta x or dx is 0.1. So our dy is our derivative, 3x squared plus 2x minus 2 dx. So if I plug in 2, we know we got 14. We already did that, but now we're going to use 0.01. So that is 0.14. So you can see, again, they came out to be very close. So that is like using a differential, a dy, versus just what is the exact change in y. And they should be very close quantities. Now let's look at kind of more of a real-life example. It says the radius of a sphere was measured and found to be 21 centimeters with a possible error in measurement at most 0.05. What is the maximum error in using this value of the radius to compute the volume of a sphere? So we need the volume equation. We know that if we are looking at the change in the radius, see it says the radius is changing at most, the change in the radius. So our dr is 0.05, and we'll put a little plus or minus to say it can be above or below, but that's the most it can be, okay? And we know that the radius is 21. If we differentiate this equation in terms of the radius, because we want to know, how the volume is changing with respect to the radius. So that's why we don't need a dr, because it's 1, you don't need it. And so we get that dv is 4 pi r squared dr. So let's plug in everything we know. The change in volume, or the differential with respect to volume, the maximum error of the volume is going to be 4 pi times 21 squared times 0.05, and we're going to put the plus or minus right here, because it can be an error because we're higher than what we want or lower than what we want. Now, if we do the math of that, it's approximately 277 cubic centimeters. So if the radius is changing just by that 5/100ths of a centimeter, the volume can fluctuate by 277 cubic centimeters, which I find kind of interesting, how this small variation can make such a big difference. And then there is your assignment work on that now. It's the odd problems from section 2.9.